And next, I'd like to welcome Mustafa Abduljabbar from Ohio State University and Hemal Shah from Broadcom to discuss the high performance and scalable MPI library over Broadcom RoCE. Mustafa is a research scientist at the Network-Based Computing Lab at Ohio State University, currently involved in several MPI 2 research projects to provide highly optimized supports for RoCE V1 and V2 Broadcom adapters. Hemal is a distinguished architect, VP, and Director of Systems, Software, and Standards at Broadcom. Take it away, guys.
Introduction. Thanks for the introduction, Phil. Can you hear me?
Yes,
everybody?
We can. Yep.
And can you see my screen as well?
Not yet.
Okay. How about now?
Yeah, there you are.
Okay, thank you. So thanks for the introduction. I'll be discussing the development of a high-performance and scalable MPI library that is optimized for the RoCE network technology. And this talk is actually a result of a collaborative effort with industry between Now Lab at OSU and Broadcom. I'm also joined by Dr. Hemal Shah from the core switching group at Broadcom, and who leads the effort on the Broadcom side. I also preserve credit to Shulei and Noah Pevek from our group at OSU. So let me start by giving a brief overview of RDMA over Converged Ethernet, known as RoCE. At the core of RoCE, it actually enables RDMA, remote direct memory access, from the memory of one node to the memory of the other node, and bypasses the OS kernel. So you see that we have a direct line going from one memory and to the other memory on the target node through the NIC. This allows for transfer of data between applications without the CPU involvement, and it enables higher bandwidth, lower latency, and low overhead communication over conventional Ethernet. So in general, RoCE is a technology of choice for HPC and AI, and there are reasons for that. Obviously, it provides enhanced performance and low latency over the conventional and existing Ethernet infrastructure, and that also implies a cost-effective solution because whoever is building the network is leveraging existing and commodity, in some cases, Ethernet infrastructure. And as the case for RDMA-enabled adapters, the RDMA operation is actually offloaded to the NIC, and that enables effective hardware-level overlap of communication and computation that happens at the foreground process in the CPU side, and of course, it provides scalability and flexibility, covering a wide range of Ethernet speeds and layer 3 routing. So our collaboration in general has been aiming to create a highly optimized MPI implementation represented by the MVAPitch library for Broadcom V2 technology. And we can break this down into two major goals. The first goal is to achieve an optimal or optimized MVAPitch CPU release that is tailored for the latest generation of Broadcom adapters. And until this phase of collaboration, we have been doing tests up to the 200 gig speed Ethernet with Broadcom Thor. We have focused on enhancing the point-to-point operations, the two-sided point-to-point operation per se, and also the frequently used collective operations, specifically all reduce and all-to-all. And we've studied the benefits of these enhancements at the application levels. And the same thing has been applied to the MVAPitch or MPI-enabled or GPU-enabled MPI with our MVAPitch GDR release series. So these are also incorporate the support for peer direct capabilities that is available in the new Broadcom adapters. And in these, we use optimized GDR copy design over peer direct or GPU direct RDMA, as well as peer-to-peer communication. So both of these high-level enhancements are to be included in the future MVPitch releases, but they are internally provided to Broadcom in the form of code drops. So on one hand, we talked about the Broadcom RoCE, and on the other hand, we have our known apparatus that is a high-performance communication middleware known as the MVPitch library. As many or some of you may know, MVPitch supports a wide range of interconnects, including InfiniBand, OmniPath, Ethernet through iWarp and RoCE, Slingshot 10 and 11, and even cloud interconnects such as the AWS EFA adapters. It's developed by the now Lab Research Group and has been there for 23 years and counting, and it's actually embraced by some of the top 500 clusters. So I will start by covering the MPI level overhead versus the IB perf latency over RoCE v2. The approach that we're adopting with this effort here is a bottom-up approach. So at the very bottom level, we studied the overhead, the latency overhead over the fabric by comparing to the results from the IB perf latency tests. So before I delve into numbers, it's worthwhile noting that it is possible to configure MVPitch with UD hybrid protocol. So for those who are not familiar with this, the transports for RDMA are generally could be RC, UD, XRC, or a hybrid of these. So we enable UD hybrid communication to reap the benefits of both transports. So we have the RC. This is the way we configure RC and UD. And actually, whenever we reference OpenMPI, we're using 4.1.4 with UCX 1.12.1, and UCX enables the communication over RoCE for OpenMPI, and also for the later versions of MVPitch 3.0 series. Additionally, for the CPU runs, we leverage the Dell Bluebonnet cluster, which features dual-socketed AMD EPYC CPUs, each having 64 core processor over 2 sockets. So that's a total of 128 processes. So whenever we reference whenever we say 128 ppm, that is actually referring to a full subscription scenario. So the nodes are split over across 2 physical racks to simplify the scenario, and we have a single switch topology where all of these 70 nodes are connected through breakout cables. So to start off with the IB perf latency. So on the left side, we have the IB level latency, and on the right side, we show the overhead that we incur on top of IB perf. We don't show MVPitch on the same curve because the lines almost overlap given the scale, the linear scale. So we have an overhead, but it's for the particular message size of interest, it is fairly negligible overhead. It ranges from 140 nanoseconds to at peaks at 16 microseconds, and that's also thanks to our optimized point-to-point parameter tuning, which I will highlight in more detail. And by the way, this was on the RC side, but on the UD side, the startup performance the initial performance that we got with UD was actually higher than that of the IB perf. On the left side, we see that the IB perf performance is 3.8 microsecond as opposed to 5.3 microsecond on the MVAP pitch side, and we have a fairly high overhead there. So this might have some impact for applications especially at a large scale when we run out of QPs. And we've only observed this issue on the Broadcom RoCE for the particular 2.3.7 series. And I will show later that this issue is not there with the 3.0 series. So yeah, so now we talk a little bit more about the latency and message rate optimizations that we applied. So to start off, usually when we are targeting new clusters, we apply rigorous point-to-point and collective tuning. So for each clusters, we build tuning tables that factor in the HCA, the microarchitecture, the interconnect, and other features of the system to be able to produce these algorithms that are as efficient and lowest latency as possible on the cluster of interest. So since we have 64 nodes on the up to 70 nodes on the Bluebonnet cluster, we have actually tuned up to 8K processes, and that's on top of the Bluebonnet CPU system as well as the GPU system that features A100 GPUs on with the Broadcom adapters. And yeah, so we've also enhanced the UD plus RC hybrid transport. As I mentioned, it actually has the benefits of both worlds of UD and RC. So to start off, we have actually optimized the switching point between RC and UD, but in general, RC exhibits better performance than UD in most cases. So we, in general, if we just compare the basic performance for a major collective such as Reduce on 16 nodes, where we have a lower latency for RC that goes from 15% lower to 33% lower latency. However, with all-to-all, the difference is not as significant as it is for Reduce. And we're able, if you look at the figure here with the all-to-all performance on 16 node and 128 ppn, we see that past the 1K message size, the RC cannot really fulfill the QP requirements. So UD can continue, and that's an automatic way that switches from RC to UD. So what we did on the RoCE adapter is that we actually tuned that hybrid threshold for the switching point from pure RC to UD hybrid. Additionally, we have our next latency reduction scheme, which is optimizing the CPU binding policy. And this technique is actually crucial, especially in many core architecture due to the complex data paths. So on the particular setup, we have opted for a hybrid spread policy. So the hybrid actually refers to the ability of allocating more than one core to an MPI process, and the spread will actually spread the ranks over the available CPU cores. So this is just showing an output, a possible output for the hybrid spread affinity policy, where we have multiple cores or CPU sets mapped to a rank. So we actually tune the policy because there are several policies there. And actually, one of the other latency reduction techniques that we apply is using a software technique to push the progress for non-blocking communication. So we spoke about the effective overlap at the hardware level with RDMA communication, but also with non-blocking communication, there is no magical progressing happening on the software level when MPI tries to pull for the updates. For these particular scenarios with non-blocking communication, it's beneficial to have some software mechanism whenever whenever it's not possible to progress communication with hardware. It is beneficial to try the asynchronous progress thread, and that's an optimization parameter that we have actually added for the 237 Broadcom series. Moving on, there are 3 other schemes that we've adopted. I spoke in the beginning about the UD performance. So one of the issues with UD was the startup overhead, which was taking a significant amount of time. So we were able to cut that overhead significantly by eliminating some inefficient calls in the critical path of the execution of the UD startup. And we've adopted point-to-point message call async, in which we combine multiple small messages to reduce the number of send and receive calls that are done at the IB verbs level, at the lower level than the MPI. So we've tuned the call async threshold or the call async limit when the call async can be enabled versus when it's disabled. And we also have a DMA-based approach, that is the scatter, gather, list, packetize, eager communication. So that has been also optimized to make the library automatically decide when that feature is to be used or when it shouldn't be used for reducing latency. So this is just showing the how much we've improved the performance with UD startup at a 4-node scale and 64-node scale from the one single process per node all the way to 128 processes per node. And we see that we can achieve up to 2.3x faster UD startup in the smaller case and up to 2.1 speed up in the larger case, in the larger scale on the loop monad cluster. Also, I spoke about the message call async. So this feature has been there for quite some time, but it's just that it has been used indefinitely. So call async has always been enabled as theoretically speaking, it seems to be an effective technique. However, if it's enabled indefinitely, one would get a degradation. Let's see if we see here at the on the bandwidth level, on the bandwidth side of things, after 1K message size, there is like 1.x degradation if the call async is enabled. So there has to be an automatic way to switch from to when you use call async versus when you avoid using it. So we have tuned the limit for using call async for bandwidth, to increase bandwidth and as well as increase bidirectional bandwidth, as we also see degradation here of 2.7x for bidirectional bandwidth when call async is enabled indefinitely. So we call that the hybrid policy, which takes advantage of message call async below 1 kilobyte message size for this cluster, but it could be a different message size for other cluster depending on the underlying hardware and interconnect setup. And the hybrid policy is also effective for the message rate. So here we show that the message rate is significantly impacted by using call async in the beginning. So it has a huge benefit when call async is enabled. However, this benefit is not sustained beyond 1K message size. So that if you look at the optimal curve with the hybrid policy enabled, it will be the best number among these two, the highest message rate among the two of the curves. And the third technique that I discussed on the latency reducing techniques is the scatter gather list for DMA communication. It's actually not as effective as the other techniques, but we get a small gain of 16% with all-to-all at a smaller scale. However, the only thing is that it doesn't really cause any degradation across any scale, so that benefit is there whenever possible. And we've enabled a parameter to disable the scatter gather list or the SGL packetizing for eager communication, in which we set it to 1 KB on the Broadcom cluster. So now that we talked about the low level or the lowest level optimizations that we applied at the point-to-point and collective level, we move on to a micro benchmark evaluation at a larger scale, as well as application level evaluation. So for the micro benchmark evaluation, we evaluate the commonly used collectives such as all-to-all or reduce and scatter. So we see, and also the latency and bandwidth. We do a re-evaluation of latency and bandwidth. So we get up to 20% reduction in small message point-to-point latency, and we get up to 2x increase in bandwidth by adopting and tuning the parameters that I discussed previously. And for OREDUCE, we get up to 12.4x lower latency compared to the baselines here, which are OpenMPI and MVAPage 237. So when I say 12.4x lower latency, I mean the comparison relative to the lowest baseline here. But the differences could not be as dramatic for other baselines. And also for the scatter, we're getting up to 5x lower latency. And we're not causing any degradation for the most part. And I will just give a glimpse of our GPU-related numbers. Hopefully in future talks we'll cover these in more detail. So, but in the interest of time, I will just discuss the benchmark level evaluation. So compared to the non-optimized version for MVAPage, we're getting 2 to 3x reduction in medium and large message point-to-point latency, and we can see that on the figure on the top left corner. And we get up to 2.6 higher bandwidth, as well as a 35% reduction in all-to-all latency, and this is thanks to optimizing the GDR copy limit. So we also have some parameters to optimize when GDR is to be used versus some other techniques over the peer direct engine on the Broadcom adapters. And here are some application level performance evaluations. So here on the left side, I have the OpenFOAM results using our Python 15.5 million cells from the motorbike dataset. We see that scalability, in this case, lower is better, and we're running up to 16 nodes. And beyond 16 nodes, we're able to run, but we don't achieve any useful scalability. Therefore, we stopped at 16 nodes. So we're getting up to 45% lower latency for this particular test case, as well as up to 51% lower latency for GROMACS with BenchPep dataset on 64 nodes and 128 PBN. So GROMACS is fairly scalable to the full cluster that we tested on. And we also test with the CP2K, with the NREP dataset, and we're getting up to 15% lower execution time, and we're able to scale up to 16 nodes, and beyond that, the scalability is broken. And we have up to 7% for WRF with 2 resolutions of 12 kilometers and 3 kilometers for the CONUS dataset. And for applications, we usually celebrate 10% and 15% performance benefits if these are coming from the communication middleware, because applications run for long times, and that means direct reduction in core hours as well as the energy consumption. So moving on, I just have some preliminary data on the 3.0 point-to-point latency latency with RC. We can see that the 3.0 series provide a competitive point-to-point performance to the baselines, which are OpenMPI and 2.3x series that we optimize on the Broadcom cluster. And we are able, with 3.0, we get lower latency with 16K at larger message sizes. And the issue with the UD has been resolved in 3.0, but we haven't done, we're not presenting elaborate application results or higher scale benchmarking, but these are just preliminary data for their point-to-point numbers. So in conclusion, we have analyzed the MPI overheads versus the IB level performance on the Broadcom adapter. So we took it in a bottom-up approach fashion. We have tuned versus existing parameters and also introduced a new parameters for the MVPitch 2.3x series or 2.3.7 series. Those include the coalescing, the use of SGL binding policies, UD startup, and other effective parameters. And we have seen that this bottom-up approach targeting micro benchmark latency, message rate, and message bandwidth has resulted in significant and at least noticeable enhancements for the micro benchmark and application level evaluations. As a future work, we will optimize for additional applications, including those coming from the DL and AI worlds. And we will be integrating these optimizations in the follow-up series from MVPitch, could be 3.0 or 4.0 series. And now we're in progress for having the MVPitch 2.3.8 that has the enhanced RoCE support, particularly for the Broadcom Thor series. And last but not least, we'll be optimizing MVPitch for Ultra Ethernet. And speaking of Ultra Ethernet, I will give it away to Hemal to cover and teach us about this Ultra Ethernet initiative from the Broadcom side. If you are here, Hemal.
Yes, I'm here. Thanks, Mustafa. So as Mustafa showed that with the MPI level library optimization, how you can realize the benefits provided by underlying hardware and transport. I'm just going to spend a minute or two just to highlight this Ultra Ethernet consortium has been started by several companies, and more companies that have been contributing to it. The idea behind this consortium, and there are already public white papers where you can see, but these are some of the key areas that with whether it's RoCE V2 or InfiniBand transport, there are some inherent challenges as you go to really high scale and high speed. So first of all, it only supports in-order placement and delivery. So these are some of the things Ultra Ethernet Consortium is trying to address at the transport layer and the application or the API level, where it enables you to do out-of-order placement, but still preserve the in-order message completion. So that's one of the idea. Second thing is with RoCE V2 IB transport, you have this go back end policy for when the packet loss is detected and retransmission is happening. That is inefficient in terms of when you specifically have high speed and several packets could be outstanding in a given message, and message sizes are getting larger. So just by having just that policy is not going to be as efficient. So what Ultra Ethernet is addressing is having at the transport level ability to selectively acknowledge the packets that are received. It kind of goes together with out-of-order placement. And this also enables you to do selectively retransmit the packets. Those are really lost. And then last two are related to network that today, the RoCE V2 doesn't allow you to explore multiple paths in the network. So by the way networks are designed, you always have multiple paths in the network to send the packets. So that at the transport level, if it gets enabled, then your packets can basically go take advantage of multipathing. So Ultra Ethernet is also cool. And all of these are triggered by today's AI ML kind of high scale, very large cluster size where people are building all these networks. And the last thing is the congestion control, which is one part which was not fully standardized in RoCE v2. With Ultra Ethernet, what it is doing is taking the lessons learned from the DCQCN, which is hard to tune, still is being deployed today in volume, to come up with more scalable and simplified congestion control. It supports both receiver-based and sender-based or some combination of that. So that's really the plug for Ultra, and all this kind of library level optimization we talked about will be valid for this Ultra Ethernet based transport. And then further tuning will be needed at the MPI level to scale to really large scale clusters. So in summary, that's what Ultra Ethernet is going towards, the high fabric utilization at high scale. And then MPI effort will be also taking advantage of that.
Thank
Great.
you, Hemal. Thank you.
Thank you, guys. Appreciate it. Okay, we are just about out of lunch break. Do we have any questions for our speakers? I did want to ask about the tunable parameters. Are these manually or automatically set for the clusters?
Okay, yeah, thanks for the question. Now, traditionally, the collective algorithm selection that I highlighted in the beginning is an automatic approach that we apply on new clusters that we target. And now we're in progress for making the rest of these tunable point-to-point parameters that target latency reduction. We're targeting making them automatic as well. Yes, so the answer is yes, it will be automatic for the most part.
Then I had a question from Rajlakshmi. How do you measure startup times for UD?
Yeah, thanks for the question. Now, so you know that we are the MVAPitch library, so we have we are actually doing this stuff by hand. So we're measuring from the MPI init side of things. So we go inside of the we have the control over the MPI init implementation, and in the steps where we're doing the UD startup by when we set up the QPs and do these connection establishment steps, we're measuring that particular area of interest.
Cool. Thank you. Are there any more questions?
A quick one about this SGL optimization. Is that using the SG list for directly for DMA at the sender side, or avoid copying? Is that something like that, or different?
Yeah, it does exactly that.
Okay, thanks.
On the sender side, yes.
Yeah.
Thank you.
Okay. Any final questions for our speakers? Okay, thank you very much. Appreciate that.
Thank you.
Thank you.
Thanks, everybody.